These are our data from the experiments. So we have on this axis, percent oil content on this axis, and the oil is in corn. So the experiments in this case took a tank of corn, and then each year they divided out some of the kernels that have the highest oil content and used those, and then others that have low oil content and used those. And what you can see is that over 100 years, of course, corn is an annual plant, so they're replicating this in one generation per year. 100 generations later, we have gone from 5% in the whole population down to around 2% in this population, the low oil selection experiment, and around 20% in the high oil selection experiment. And we can look at this data from another angle. This is the original data here, around 5% on average, fairly narrow distributions, and they were able to jack it up all the way to 20 for the high oil content and down below 2% for the low oil content. So this is a nice example of how you can select on this quantitative trait and really change the phenotypes over time. It doesn't show a lot of variability in here, but in fact there's a lot of hidden variability. And of course, over the time of this experiment, there's probably a lot of, at least some opportunities for mutations to have an impact as well. So probably some of this change or this change is due to mutations, but much of it is probably due to simply to selecting on and sorting on the multiple genes that go into making up oil content. So it's a multi-quantitative thing. So what we're going to talk about today is a little bit about how breeders and others that are interested in artificial selection are able to quantify and predict these sorts of results. So the key is an idea called the breeder's equation. Pretty simple mathematics. Essentially, the response to selection R is equal to the narrow sense variability, of H squared, multiplied by the selection differential. So it's a simple equation. Let me see if I can navigate you through this figure. So basically, we have three examples of selection. Okay. And in each of the panels, we have the phenotype on this axis, x-axis here, and then these are our normal or paranormal. And they may be distributions; they look fairly normal. The parental generation is in black, and the offspring generation is in red. And basically, the key, these variables are all hidden in these panels. So this is the phenotype of the parental population. I'm sorry, the mean phenotype of the parental population here, right? That's the average of that. What they did in this example is they read all individuals that had a value of phenotype value of 12 or higher. So the red ones are the ones with red, and the offspring are from this breeding. In this individual breeding, the offspring are described by this other. So we have the selection differential here, this distance between the parental population and the ones that actually bred. And one thing to keep in mind is that, well, looking at this panel, we now have the parental population here, the offspring population here. And really, this, in some ways, this is, these curves are a one-dimensional snapshot of this figure. So if you were to take just the mid-parents and calculate the distribution, it would look like this distribution. So again, this average is here and the average is here. So what happens when we actually do these experiments, right? We're taking the selection differential here. These are all the parents here, right? This is the ones that are actually odds to breed. And so this is the selection. And then the response to selection is this distance here. Now the key between the different panels is where the variability lies. So in this panel, remember variability. How do we measure narrow sense variability? Anyone remember? So variability in the narrow sense is the slope of this regression right here, or this regression, or this regression. So it's the effect of one unit change in the parent phenotypes to one unit change in the offspring phenotypes. So it's the slope of that line. And so what happens with the Breeder's equation is you're literally taking this distance here, s, right, which is this, you're multiplying it by the slope, and you're getting this value here. So if the slope is 1, as it is nearly here, then the response is just about the same as the selection difference. Right? So you select these individuals and breed them, and the response is just about as high. But here where you have lower variability, okay, with the slope, a squared, r squared, is lower, then basically this distance multiplied by something shallower than 1, so the response is smaller. You with me? So again, the black distribution is all of the parents. This distribution here. The red bit here is the mean of the ones that were allowed to breed, so just the very largest or highest trace value of the parent. And then the offspring are these offspring here, and they are this much higher than the
Candid, we're going to make exam in this chair. See?
From the parental to the offspring, given selection.
I have only one. I'm going to send it to you.
It is the difference between the predicted mean here, the mean of the mean that would come from if you bred all of the parents here. But you're only reading a bit of them here, and therefore the actual observed response is up here.
What?
So if there were no selection at all, right, then this value, this mean would produce this mean here. So these are the two means of the population. Offspring mean without any selection. Parent mean. Okay. So if you only allow some of them to breed, then you get this shift here. And importantly, the ways that these differ, so here we have a lower slope, so less variability, so this number is smaller, therefore the whole response is smaller. Here we have a bigger selection differential, right? You want to take a smaller slice of these, of the parents, and that's going to push the response further, so that's why the response is further up. Question? So the key for you to remember is we'll see lots of these figures. These figures, and we're going to look at our own data from the selection from the selection workshop, the measurements that we did on height and handspan. And we'll see that we can measure variability in this grow as well, which means that we could probably predict if we want to grow people with larger hands. Okay? Now, let's take this and apply it. So here's an example. Again, the same thing we started for. So the Breeder's equation is just R equals, the response is equal to variability times the selection strength, right? And in our example, what do we have? We have a heritability heritability, we're given a heritability of 0.5, and the selected fruits on average are 2 grams heavier than the population as a whole, then what would we expect the response to selection to be? Did I just have to do the math?
Oi. What?
What is it?
I don't. What do you think?
What's going to be our response to selection?
How come? I don't know.
The selected fruit is 2 grams heavier than the population average as a whole, what should be our value?
It's not on here.
Well, let's see, heritability is 0.5.
It's
It's
square.
not on there.
The edge.
And what's our selection?
No. 0.5. Should be B, right? 0.5 square.
Sorry.
And then
Squared is actually,
S is 1.
is actually heritability. This whole thing. Yeah, sorry. Yeah. So H squared is actually
Oh, so it's not the one, yes.
I looked at the page, I was like, am I going crazy? Is that on there?
So,
No, I just put it
so H squared. Well, little h. Don't worry about the h. H squared is the value of the okay? Rocket narrow sense heritability, and it is 4.5. That's yeah, the equation is simpler than it looks. It's H squared is just a thing, it's just heritability. Okay? So we can do this, right? We can also we can calculate our response to selection. We can also find a heritability if we know what the response to selection is, right? So here we have another example, parental population of turtles with some phenotypic value of 0.6. The selection, after selection, the phenotypic value of 0.8, right? So these are selected. So we can figure out, and then of course the offspring selection generation is going to be a value of 0.72. So we should be able to figure this out, right? And this is just the basic algebra. Someone want to talk me through it, or should we do it? Why don't we take a wild stab at it first?
But what is P?
So what's the yield?
It's just a parental car. Oh no.
No, I did it.
Oh yeah, yeah. the selected color in the offspring value.
So what do we know? We're trying to find what?
But where is the
So we want to know heritability, right? So that's our question.
so R over
And
S? What is the R?
we're given F. What's F? So what's the selection difference?
28. 28.
What? Yeah.
The difference, right? So it's the difference between this and this, right? So it's a plus 0.2, right? What's R? The response. 0.72 is the new value, and that's the shift from this, right? From 0.6. So that's 0.12. I'm sorry. Yeah. 0.12.
Do you get that?
How do
So, and what do we want? We want h squared. So h squared
how did we
equal
get
to r over
point
x.
or oh yeah, yeah. We subtracted offspring minus penta.
The change.
But there's
Yep,
two
the response,
parentheses.
both the response and s.
No, there's only one.
There's parental 0 and parental 1.
Yep. So what should this be?
The first is parental and the third one is the offspring.
What's the middle?
So it's
Selected.
0.12 divided by
So 0.6 minus 0.72 is 12.12.
0.6 minus
0.6, right?
0.7,
7
Am I doing the math right?
0.12, and what is that, R?
Yeah.
He said,
R, yeah.
So heritability is 60%, or that's for
Wait, how did he get the 0.2 though?
subtracted from parental minus selected.
So why is he subtracting that now?
To get the selection.
That's a little weird. And then,
You guys with me? So R is the response to selection. So this is the parental generation before selection. This is the offspring generation. It says before selection, but it's just the offspring, right? So we took all of these, we selected some of them that had a higher value, we bred them, and we created these. They have a higher mean value than the original mean, but it's not as high as the ones that we selected, right? So basically, this is heritability is just a proportional increase that you get relative to what you thought you had, right? So if you read all of these that have a value of 0.8, if it were perfectly heritable, the offspring would all be 0.8, but it's not because there's noise in there. Some of these have this really dark phenotype just because of environmental variation. Okay? Some of it turns out about 60% of it is due to additive genetic variance. Right? 40% of it is due to just environmental effects.
Wait, Professor, why did you subtract to get the R? You subtracted the offspring
Well,
line.
the response to selection, let me go back and look at this. So, let's look at this figure here, this panel. So, imagine for a minute that none of the dots are colored, okay? In that case, you have all of this variability here in the parent, and if you bred them, these are the offspring that you would get. The dots are all what would be observed without any selection happening, okay? Now, if you breed only the ones with the very highest phenotypes, then their offspring are going to be respond. They're going to have a higher value up here. So the figure is really showing you the mechanics of the equation, because this response is literally this distance multiplied by the slope. Imagine the slope were flat. If the slope were flat, then heritability would be 0. There would be no response, right? Even if you breed the very highest valued organisms, you wind up with no effect whatsoever. In contrast here, in either of these, heritability is super duper high, right? So basically what you see is what you get. If you breed the ones with the highest values, you're going to wind up with a very strong response. So if we go back to the turtle example, then with a slope of 1, or heritability of 1, you'd expect that if you breed the ones with a value of 0.8, that's what you get. You get 0.8 in the offspring. but in fact, you only get 0.72 if it's not heritable. It's invisible. Only 60% of it. And that's what Peter's equation does. It tells us that if you have some amount of heritability, something between 0 and 1, and you select away from the average of the parental population some distance, then the response is going to be that distance proportional to the heritability. With me? Questions?
Still didn't answer.
All right. So, paradoxically, heritability of corn in this experiment declined throughout the lifetime of the experiment. So, heritability initially in 1897 was around 0.4. But by the end of the experiment, we're down to getting touching 0, right? Sometimes it's negative. Thoughts on why that would be? It's, as I said, it's paradoxical. So, traits that are more strongly correlated with fitness tend to have lower heritability. So in this case, those oil measures are super highly correlated with fitness because the breeders are selecting them, right? So really strong selection based on those characteristics. What happens when we have very, very strong selection is that the alleles for those quantitative traits start to get fixed. You lose variability. And as a result, you lose genetic variation at those different loci. So you have a bunch of different loci that affect the oil content in corn. You keep selecting for the high oil content phenotypes. Eventually, that's all you're going to have left. You're going to have only genes at those different loci are all going to be the high corn alleles. Now, and so I'm going to show you a figure that shows you actually why this is. But it's important to recognize that this is true for the corn experiment because it was artificial selection and very strong. But there are lots of life history traits also that have really low heritability. And that's because life history traits can have very strong effects on fitness. And by life history, this is what we're going to talk about a week from today. By life history, we mean things like how many offspring do you have, how long do you live, how old are you when you first treat, things like that. Because those things have really strong effects on fitness. Now, this figure shows us what's going on in that corn experiment, and also with these life history traits in general. So, remember, this is our measure of heritability, right? It's the total variance, or the proportion of variance rather, that's attributable to additive genetic variance. So it's the variance that's visible to selection, right? And when you selected out all of the variation that you have, when the corn is just high oil, or you select it the other way and it's just low oil and there's no variability left, then the genetic variability goes to 0. And all that you have left is environmental variability, and 0 divided by 0 plus something is going to be 0. And that means that when you start looking at those corn today, after it's been bred for 100 years, you wind up with a flat slope. So there's still variability in the parental corn, but even if you select the very biased ones, you wind up with no change. And that's because there's just no variability left. All the variability that you're seeing is environmental variability. There's nothing genetic left to select upon. And that is why we would expect it to decline over time. Questions? Okay. Let's see. Talk for just a brief just a minute about the heritability workshop, with heritability. So all of you submitted some data that looks something like this. There we go.
Yes.
And this is what we found. So this is height, mid-parent height, offspring height. We were one of these dots. So what's the heritability of height? Anyone?
Head.
1.016. That's right. So it's 1. So height apparently is profoundly heritable, which is really interesting. I would point out that there was some funkiness in the data that I had to deal with. As far as I can tell, some people measure height in feet with no decimal place, and at the same time measured handspan in centimeters. I think, I'm not sure. Or maybe they were measuring something else. Some people had handspans of 20 inches. But anyway, I tried to get rid of some of the crazy values systematically, and others I just threw out because they were too crazy. But anyway, we have data. So here's some data. There's more data. So this is what handspan looks like. How heritable is it? More or less heritable, apparently, than
Less.
less heritable. It's still might be heritable, which is pretty amazing.
That's like 2.5 minutes.
And then I also, just for the fun of it, I looked at the ratio of the two. So height as a function of handspan. So these are, so if you have a handspan of 8.5 inches, more or less what mine is, that means that you would be what am I trying to say that is yeah, that I'd be 12 times 8.5 inches tall. Right? Whatever, I'm messing up the math. I just did the ratio, whatever it is. So height as a function of hands. Anyway, again, heritability super duper high. Not clear how much of the team really like some of these crazy outliers here. Yeah, but anyway, there we go. So there is, or will be shortly, a quiz up on Moodle. It's going to ask you about figures and you can work them with, put up some ideas about why we found the bubble. But before we do that, I'm just going to go ahead and do that. All right.
Wait, Prof, I have a question. What happens if heritability is not correlated with fitness?
Come again.
What happens if heritability is not correlated with fitness? What happens then?
So the question is, what happens if heritability is not correlated with fitness?